So, hi guys, and welcome to our first chemistry video lesson. Today we're gonna continue from where we were left off. We were doing, we were on covalent bonding. We were doing giant covalent structures, and we were on carbon. So we were doing the forms of carbon, which we will know what they are called. We done diamond. Now we're gonna do graphite. And we're gonna watch a video in the end about diamond and graphite. Let me first explain you what are these video lessons. So you're gonna listen to these video lessons, you're gonna listen to me telling you the lecture, and you're gonna write whatever you see on the slides. Each time the slides are gonna go in stages. So if the slide page is gonna be filled when I progress through the topic. So when the slide page is filled, you're gonna write everything on the slide page down to your notebooks, and you're gonna have to draw the structures that I tell you to draw to your notebooks as well, which is important in this topic. To start with, let's do a little bit of revision. You're gonna write these down as well. You can stop the video anytime to write the lecture to your notebooks, and you can watch this as many as you want. That's the advantage of this video lesson. So let's start. So covalent bonding, giant covalent structures, allotropes of carbon. The one we're gonna do today is graphite. So diamond, graphite, and fullerene, they're all forms of carbon. Okay, the main the main structure of these, the component of these structures are just carbon atoms. So they're all forms of carbon. They're not molecular structures, but they're giant covalent structures. So they're not actually molecules like an oxygen gas, O2, or a hydrogen gas, H2. They are different structures. They are not considered molecules because their numbers, the number of atoms, is variable. It's not 2 or 4. It can be 60, it can be 20. It can depends on the size of the diamond or the graphite or the fullerene. So we don't call them molecules. We call them giant covalent structures. So you can see a picture of these three different forms. The first one is, as you know, is diamond. Second one is graphite, and the last one is fullerene. So graphite is another form of carbon. Differently from diamond, in graphite, carbon atoms are in a layer structure instead of a tetrahedral arrangement. So you remember the 3D structure of the diamond. Here instead of that 3D crystal structure, you have layers laid on top of each other. You can the structure of diamond is really similar to a deck of playing cards. So you have layers that are formed with covalent bonds between carbon atoms, but between those layers you have weak forces of attraction. So you can separate each card, which means each layer, but you cannot separate the card into two. It needs more force. You can imagine the arrangement in graphite like a deck of playing cards. Each card is strong and hard to break, but individual cards are easily separated. So a recap of what I told you. In graphite, the carbon atoms in a layer are held together by strong covalent bonds, but there are only weak forces of attraction between these layers. So this makes graphite a soft material. So like the layers, they can separate easily. Graphite most commonly found in your pencils. If you have written down with a pencil before, so you know when you lay your pencil across the paper, it leaves a black line. It leaves a line of graphite. These are the actual layers that are left behind because you don't need much force to separate the layers. That's why you have a layer of layers of graphite left into your paper each time you use your pencil. So write these down and also draw this structure into your notebooks. Don't worry about, so just draw a couple of these structures. Don't draw everything, but write down the labels. So strong covalent bonds between the carbon atoms in each layer, and also the weak forces hold the layers together. So a recap, just like I said, it's really hard to separate the covalent bond, but the weak force between layers are easy to separate. So if you have a deck of cards, you can separate the individual cards easy, but you cannot separate cards into pieces. It needs much more force, basically. So like I said, pause the video and write these down. I'm just going to remind you one time, and you have to do it every time a slide is finished. Okay, so carrying on. So properties of graphite. The layers separate easy because of this. Graphite is soft. This is why it is used in pencils or as lubricant. So like I said, you can separate the layers easy, so it's a soft material. It's not hard as diamond, basically. Graphite has a high melting and boiling points. Graphite has high melting and boiling points. Although the layers can be separated easily, to melt graphite we need to break down covalent bonds between the carbon atoms forming the layers, which need very large amounts of energy. As you know, covalent bonds are really strong. So like I said, in order to separate the individual carbon atoms, you need a lot of energy. Because of this, graphite has a really high and melting and boiling point, just like diamond. Okay. Graphite can conduct electricity. If you look at the molecular structure of graphite, you can see that each carbon atom bonds with 3 other carbon atoms. This means that each carbon atom has 1 free electron in their outer shells. As you remember, carbon atoms can form 4 covalent bonds. These free electrons are called the localized electrons. Okay, so as you remember, carbon can form 4 covalent bonds in order to have a full 8 shell, a full shell with 8 electrons. So in graphite structure, you can see that each carbon is connected to 3 other carbons. So it forms 3 covalent bonds. But it actually has 1 extra electron in there that is free. That's how it is able to conduct electricity. So these delocalized electrons allow graphite to conduct electricity. So today, end of every video lesson, we're gonna have a video to watch. So let's watch this video, and I will pause it to comment about it sometimes. It's about graphite and diamond. Okay. Yes.
In today's video, we're going to learn about the structure and properties of 2 allotropes of carbon, diamond and graphite. And we'll consider the other allotropes, graphene and fullerenes, in the next video. First though, you might be wondering what an allotrope is. Basically, allotropes are different structural forms of the same element in the same physical state.
So, for example, like diamond, graphite, fullerene of the carbon. They're allotropes of carbon. Allotrope means is different structural forms of the same element. Okay?
So if we consider carbon in the solid state, it can take lots of different forms, like diamond, graphite, or fullerenes. So these are all different allotropes of carbon. Both diamond and graphite are giant covalent structures, which means that they're made of a regular lattice of covalently bonded atoms, which makes them both very strong. In diamond, each of the carbon atoms is covalently bonded to 4 other carbon atoms, which is the maximum number of bonds that carbon can make. This forms a regular 3D pattern, which you're fortunately not going to have to draw, but you do need to be able to recognize this sort of structure. As each of these covalent bonds is really strong, it will take loads of energy to break them, and so diamond itself is very strong and has a really high melting point. However, it doesn't conduct electricity because it has no free electrons or ions that can move around. Now let's compare these features of diamond to those of graphite. First,
So as you remember, diamond had a really high melting and boiling points. It was strong. It was the hardest material naturally occurs, and it doesn't conduct electricity. This is because of the structure. Actually, each carbon atom is connected with four other carbon atoms, and then you don't have a free electron. But in graphite, as you remember, there was a free electron which is able to carry the charges, so it can conduct electricity. Let's carry on.
Each carbon in graphite is bonded to only 3 other carbon atoms, rather than 4 in the case of diamond. Second, the atoms are arranged into hexagons that together form large flat sheets, which are then arranged on top of one another to form lots of layers. However, these individual layers are only held together weakly, as there are no covalent bonds between them.
So imagine a deck of playing cards. Like I said, it's a layer structure.
This means that they're free to slide over one another, which makes graphite relatively soft when compared to diamond. That said, graphite still has a very high melting point, because the individual layers are strongly held together with covalent bonds. Now, do you remember how earlier we said that carbon atoms can make 4 covalent bonds each, but in graphite they only make 3? Well, that means that each carbon atom in graphite has 1 spare electron that it's not using in bonding. Instead, this electron becomes delocalized, which basically means that it's free to move around. And all of these free electrons allow the graphite to conduct electricity and heat. Before we finish, it's worth mentioning that a single layer of graphite is known as graphene, and scientists can actually isolate these individual layers and use them to make other structures, such as spheres and tubes. We call these structures fullerenes, and we explore how they work in the next video. Anyway, that's everything.
Yes, guys, so the video actually mentions the single layer of graphite, which is called graphene, which actually can be synthetically used to form fullerenes. So that's the topic of our next lesson, and we're gonna do fullerenes in the next lesson. A couple more things about this video lesson. So you have to write down everything, because this is actually considered your course material. So you have to write down everything on the slides, and you have to basically listen this as a lecture. But the good time with this, you will have the link, so you can, anytime you want, you can come back to this video and watch it again and again. You can watch it for revision, or you can just watch it a couple more times to make it fit better into your heads. It's up to you, but you have to do this in 24 hours, so you have time until the next evening, so to say. Anyhow, thanks for watching, and hopefully we will see you soon at our school. Okay, bye bye.